Yeah, that's right. Well, the future is always hard to predict. You know, what can you do? Flying cars, yeah. Yeah. So everyone here knows that today's stuff is not going to be in the final exam, right? So you're still here. Good, right? Very good. Anyone has asked me for remarking? I have some remarked results. What's your name? Yeah? We can talk about this if you have any questions about it. Anyone else? Remarking request? We are not going to have a very long lecture today, maybe an hour and a half. So we'll just go straight through instead of breaking it up into two parts, okay? This is two. Yeah. So far we have talked about validation, and we saw that we can use validation to estimate the actual performance of a learning model doing testing, doing inference. So we saw that, that estimation could be very good. Yeah, we have some analysis on that. And then we went into this special topic of model selection by validation. Right? The idea is that we have many different models to choose from. Each one of them is represented by a set of hypotheses, right? H1, H2, and so on. Could be linear hypotheses, quadratic, and so on. Okay. The question is which one is better, right? And you can use validation to choose. Yeah. And the solution looks like this. What we have seen last time. That's as well. You use the training data set that you reserve only for training to train this m different models, and then m different models, yeah, to pick the best hypothesis within the model, and then you use the evaluation data set, the validation data set, to evaluate the performance of those best hypotheses that you pick out of each one of these models. And then you pick the minimum among this validation error, of course, right? And then you pick the best one among them, so that's your m star. Yeah, m star is the best model among these m models. Yeah, and then you retrain this m star model by using the entire set of data. Yeah, in order to get the final result. So the question then is, does it really work? Does it really work well? Yeah, and what are the potential concerns?
Being connected.
So of course, what we want. Oh, I'm sorry, I pressed the button by mistake. Thank you. What we want is that this validation error for the GM star that you pick, yeah, is approximately equals to the test error for the same GM star minus. But this one should also be approximately equal to the test error for the final one that you get, right? The GM star without using validation data. And we already know that this one, of course, will be true if k is small. Yeah, right? Clearly, if you don't have any validation data, then those two will be the same. The question is this always true? Yeah, this is the best one that you pick. So it turns out that the analysis is very similar to what we have seen before. So to some extent, this analysis will be almost like a review for the final exam, right? And so one thing we note is that if you look at any m that we pick, not just m star, any m, any model m, you do this, and you check this validation error, yeah? And that m will be picked independently of the model selection. So for any given m, let's say, yeah, that's in 1 to m. In other words, this is picked before model selection. Maybe this should start to remind you of something that we have seen before, yeah? Before and after. Yeah, we have done some similar analysis before. Yeah. So this is because it's picked before the model selection, just any m, right? So now we're just saying that this is just a regular validation, right? Yeah, just a model, you use validation to check the performance, yeah? So therefore, from previous analysis on validation without model selection, on validation, just simple validation on a single model, we know that the expected value of this validation error, GM minus, is really equal to the test error, right? It is an unbiased estimate of the test error, yeah? It's just validation on one model, which we have already shown last time. And also the variance goes to 0 if you have enough validation data points. That's because the variance equals to the average of the variance of the per sample error, right? Yeah. Again, this is nothing new, right? We have already shown this last time. So this is a consistent estimate. We have unbiased and consistent. And also we have a Hoeffding bound if your error is of the binary form. Yeah. This upper bounded by the validation error. So this is just review for what we have seen already. This is the part that would be on the final exam, potentially. Yeah. And this is, again, if this error function is actually the indicator function, yeah, for the case of classification. So, but this is for the case of any model M, yeah, picked before model selection. The question is, what we want is actually for the M star again, right? M star is the one that we want on top there. And that one is actually picked after model selection. Okay? So therefore, it turns out this analysis does not work anymore. Just like before, remember before when we say, is E in approximately equal to E out, right? In the 2 weeks back when we studied that over there we have a E in of what? E in of which hypothesis? Any randomly picked hypothesis, or the trained hypothesis, the final hypothesis that you have trained already, pick the best one. Those two analyses are very different, remember, right? Yeah? So this is exactly the same here. Here it says that if you just pick any arbitrary model, well, we still have these nice bounds. But then when you talk about the best hypothesis that you pick, M star, using the validation data, now that best M star and the GM star depends on this validation data set, dval again now, right? So this cannot work anymore. Okay, we introduce dependency. So one has to be very careful about this kind of analysis. Yeah. So what can we do? So the trouble is that this does not work for M star. m star minus. Yeah? Since we have chosen hm star using the validation data set. Okay? So in other words, gm star minus is not independent of the data set. But how do we deal with this? How did we deal with this before? When we look at the relationship between E in and E out, whether that hypothesis for which you are evaluating E in, is it just some randomly picked hypothesis or the final hypothesis? How did we deal with that? Remember what we did before to deal with this? When there's dependency. Union bound, yeah. We use union bound, okay? Same thing here, turns out, yeah? So the solution is union bound. Again, yeah? Okay. We can use the union bound because we know that this hypothesis that you pick has to be one of those m of them, right? G1 minus, G2 minus, to Gm minus, right? It's one of those guys, yeah? Kind of the so-called quote-unquote best one among them. Yeah. So therefore we know that if we want to find the probability that this E validation error, m star minus, subtracting the test error, m star minus, this one to be greater than some epsilon, yeah? Well, basically, you want this probability to be small, right? You want those two to be close. This one is less than or equal to the probability of the union of all of them, so m equal to 1 to m, this eval gm minus e out gm minus, yeah, greater than epsilon. Right, does everyone agree? Yeah. Well, this is because this event, because we know m star is one of these m's, right? So this event must be inside here. Yeah, this must be inside here. This set must be inside here. So therefore, this is a subset of that. Therefore, the probability has to be smaller. Yeah, it's a subset of this union set. Now, since we have probability of a union, we can use the union bound, right? So this is a by the union bound, this is less than or equal to the sum of the probabilities. Gm minus epsilon. Yeah, right? And now, of course, each one of them, this m is just some arbitrarily chosen m, right? Just arbitrarily chosen m. Therefore, the previous bound holds, yeah? The previous bound here, say the Hoeffding bound holds. So each one of them has the same Hoeffding bound, right? Therefore, we have 2 times m times that Hoeffding bound, which is e to the minus 2k now, because instead of m, yeah, because we have k validation data points. Yeah. So again, you can have a upper bound. So in other words, this implies that for any, say, delta greater than 0, with a probability greater than or equal to 1 minus delta, we have the following bound. That's based on both Hoeffding and union. Yeah. Gm star inverse, minus inverse, E validation plus 2k log of, instead of 2, you just have 2m, that's all, right? You have to relax this bound by m over there. Yeah. And this is for if you can use the Hoeffding bound, you know, when you have classification, you have Bernoulli random variables. But in general, you can show that the same scaling holds. Yeah. E out. Big O of log of m over k, like that. Yeah. So which is very nice, right? It says that if you have large enough number of validation points, then this optimally picked model also gives you this nice equivalence, near equivalence between the validation error and the test error. So model selection by validation does seem to work in this sense. Yeah. So of course, this one requires k to be large, and the other side will require k to be small, right? So again, we have this trade-off around k, trade-off by k. That, well, remember we want the eval of gm star minus to be approximately equal to e out of gm star. Now we know that this is when k is large, yeah. But we also want this to be small. In other words, we want the case without validation, yeah. Those two test errors to be small, to be similar as well. But this only works if k is small, yeah. So we have a trade-off there on k, and in general, again, you can say, well, I'm going to pick 20% of my data points for validation, and 80% of data points for training. You could do that, yeah. But you still have to consider, yeah, what is optimal k in general. So in general, you can see a picture, the figure looks like this versus k, and the error that you get out of your experiments. You know, say if here, this is the, let's say here is the error that you get from just combining all of the models together, just train all of the hypotheses that you have. Yeah, remember this alternative, you can always do that, right? When you have all these choices, you know, combining all possibilities. So directly training NH, which is the union of all of the possible models that you can consider. Yeah? Well, of course, this is without validation. Yeah, so it's just a flat line, yeah, doesn't involve k. In that case, then turns out that if you do model selection by validation, your E out of GM star minus roughly look like this. It goes down and then it goes up. Can be on even. Yeah. So this is the E out of GM star minus, like that. Well, I'm going to move it a bit to the right because I need some space there. But turns out that if, remember we don't just use GM minus, right? We retrain the model M star model using the entire data set. In general, because you have more data points, assuming that you have enough computation power to handle these data points, you will do better. So this one will be the actual one that you get. Yeah, well, it still picks up at the end, but you know, it is better than the previous one. So this one will be E out of GM star, like that. Okay. Why does this two curves look like that? On the side when k is small, why are they so close? That's what we should expect, right? If you don't set many points for validation, then roughly GM star minus and GM will be the same. But on this side, why are they different? Well, again, this one is when you have more and more validation points, the GM star minus would not perform as well anymore. Yeah. But interestingly, in general, if you use too many points for validation, your performance can be actually worse than hierarchy training without validation. Why is that? Why is also not good to use K2 high? Why is that? Well, because you don't have enough training data points left to find a good hypothesis. Yeah. So whatever hypothesis you get for each model is not accurate. And then when you choose these models, that model selection is also not accurate. Yeah. So in the end, you don't get good results. So there is this trade-off around K, right, for this method in general. But now the question is, can we do without this? Can we alleviate or avoid this dilemma? Yeah. So, and the answer turns out to be, yeah, we can do that with cross-validation. Cross-validation, it's again to avoid the dilemma. Yeah. The dilemma over K. Yeah. And so in practice, that's all that we do, pretty much. Yeah. Cross-validation is the most popular validation method instead of the previous one where you set aside, say, 20% of your data points. And let's first talk about the leave one out cross-validation. Leave one out, or the LU cross-validation. So just from the name, leave one out, this is one data point that you leave out. Yeah. So basically, you split your data point D into two parts. The validation part only has one data point in it. The training part has n-1 data points in it. Okay, a lot of data points for training, but only 1 point for validation. Then you think, well, how does that possibly work? Right? That's 1 point is not enough for validation, right? So what do we do? But let's write this down first. So we have the training part, leave some space in between, and then we have the validation part. Yeah. Validation part is one sample. So let's give you a notation. This one sample, let's say it is xn, well, let me use blue color, maybe fancier. Xn, yn. Yeah, this one data point. That means whatever is left for training n-1 samples, and the notation, we use dn for it. Yeah, dn. Of course, it's just the remaining ones, right? From n1 to x1, y1, and these xn, yn. In fact, you're going to cross it out, right? You take it out, yeah? Just leave it out. But the rest, they're all there, all the way to xn, capital N, yn. Yeah, so that's what's remaining for training. And you're going to use this training data set, of course. Again, send into your learning algorithm. And then you get this G minus, but we're going to call it Gn of minus, just thinking that this is a training result after you've taken data point n out of it, yeah, the nth data point. So of course, this will not work very well if it's just this order you do, right? One data point is not good enough for validation. The idea is that you will do this for n times. And you do many times of this and take the average. So you do validation. So the validation error for this 1 point error with respect to this data point n, we denote it by en. Yes, it's simply our previously defined validation error. Yeah, just like that. Since one data point, right, the average is just the error of this one data point itself. Yeah, xn, yn. Yeah, like this. So we're going to repeat it n times and take the average of this en in order to get a good estimate for the validation error. Yeah? Repeat for n equal to 1 to n. Now you have E1 all the way to En, yeah? Right? So now we can define the cross-validation error or cross-validation estimate. We call it ECV, like that, is the average of these n's. Like this. Okay? So this will be our validation error. Okay? So every time you just use one, but then you do this many times and you get a nice average out of it. Now, so let's take a look at an example. How this works. Suppose we have a linear classification, linear regression. D equal to 1 makes things simple. And let's say you only have 3 data points in your data set. So ECV, of course, it would be 1/3 of E1 plus E2 plus E3. Yeah? And let's look at one example of this. We have 1 point, say 1 point here, let's say 1 point there, and then a slightly higher point over here, like that. Okay? And this location, of course, will be x1, x2, x3, right? These are the location of 3 data points. Yes?
So when you say like a repeat, do you mean like we retrain the whole model n times?
That's right, yeah. Yeah. We can improve on that, but let's leave that in about 15 minutes. Yeah. So in this example, we have 3 data points. Yeah. So how does cross-validation work for linear regression? So first, we take out one of the samples for validation and train using the rest, right? So we take out x1, and then we have only those 2 left. When you take out this one, those 2 left for linear regression, what is the solution for linear regression? Again, this is the final exam review now, right? Just a line connecting these 2 points, right? Linear regression on 2 points. Yeah? So it's very simple. So you just have a single line going through these 2 points. Let's say it looks like this. Well, I'm going to change my point to fit this line. Why not? Let me make this a bit, extend this a little bit. I'm cutting x1, that's not good. I was afraid of that. All right, x1 again. This will be x1 location. Yeah? This line would be, of course, the line corresponding to the case of n equals to 1, right? We'll take out the first data point for validation. Yeah? The remaining 2 points, linear regression, you get this line. Yeah? What is the E1? Where is E1 on this figure? The estimation error. Yeah? The line gives you the prediction, which is right here. Yeah? But the true label is down up there. Yeah? So therefore, in this case, the error is here. This is E1. Yeah? Now, let's do another one. We have to repeat, right? Let's repeat. N equals to 2. We take out the middle point. Yeah, then we do linear regression using the remaining 2 points. So, well, the line looks like this. Yeah. So this is the line for n equals to 2. Yeah. Very better. Okay. And the error, of course, would be between these 2 locations. So this is E2. Yeah? And the third one, it's pretty easy now, right? Take out the third one, and then you draw a line connecting the remaining 2 points, like that. And then if you want to know E3, then E3 is here. Yeah. Well, this is the line for n equal to 3, and this is E3, like that. Okay? You take the average of these three, that would be your cross-validation error. Yeah? Now, suppose we want to do model selection based on this. Let's look at an alternative model. How about constant regression instead of linear regression? Yeah? Just always constant values. Okay? You know, in exams, we always use this kind of toy examples. Or in class, right? We don't have a lot of time. In homework, you might see things takes a bit more time, but other places we use sillier toy examples. But I think it does give us some interesting insights. I think around like that, right? Yeah. Okay. So now consider. Oh, I did not say. Let me move this down a bit. I want to say this is a. Let's consider constant. So same as previous, except that we want to consider constant regression. So x1, x2, x3. Yeah. What would be the first line be? What would be line 1? Again, you cover up the first point, the other 2 points. When you have 2 points to do constant regression, of course, the line will be right in the middle, yeah? Right in between those two y values. So I would say around here looks reasonable. Yeah. So this is n equals to 1, right? What is E1? Oh, look at that. E1 is tiny, right? This is E1. Yeah. And line number 2 will cover up the middle point. The line probably looks something like this. Yeah. This is n equal to 2. Yeah. Well, E2, this one is a bit bigger, but similar to the previous case. Yeah. This is E2. Right? E3, cover up the third one. You draw a line in between. Everyone okay with this? Why do we drawing these lines? Yeah. So this is the line right between point 1 and point 2. The labels of point 1 and point 2. So this is n equals to 3, right? And E3 is here. Right? Yeah. So if you compare these two cases, which model will you choose? Clearly the constant regression, yeah? Smaller cross-validation error. So this one has smaller ECV. So we have a constant regression is preferred. Okay. So, well, this is assuming that you believe that this cross-validation error is a good measurement of the test error, right? So is that true or not? Yeah. So we have to be a bit careful with the analysis. Yeah. Does cross-validation really work? Yeah. So one thing to note is that this cross-validation, of course, is the average of E1, E2, and so on, the EMs, right? So EM, this per sample cross-validation error, it's just per sample cross-validation error, just the regular validation error, right? With a single data point, yeah? When k equals to 1, basically, right? EM. So it is, of course, an unbiased estimate of the test error. N minus, anyways, yeah? It's this one. Okay. How to, well, again, we know this because there are two ways to show this. Yeah, one is simply saying that, well, this one single point validation is just validation. Yeah, k equal to 1, right? So this is just a so-called basic, let's say basic validation. Yeah, and we have to show that the basic validation is an unbiased estimator of the test result. Yeah. Another way to do this is to just show it, mathematically, just prove it again. It's not so hard. Let's take a quick look. So we're taking expectation of this over this one sample that you pick, right? The value, which is random. Yeah. We want to show that this expectation equals to the test error, right? So this is xn, e of g minus n, xn, yn. Yeah? This is just the whatever error function that we have, square error or Bernoulli, doesn't matter. Well, if you look at this expectation here, the randomness on xn, and inside the errors also only involve xn, right? I can replace this xn by any data point. This will be the same, right? Because all of these data points are identically distributed. Yeah? I can change this n to anything. In fact, I don't even have to write n, right? Just general that distribution of the data points, the general distribution from which you pick your data points. So I'm going to write Ex like this, Gn minus x, y, right? In particular, this x can be the test data point, right? Yeah? This x can be a test data point. And in that case, then this simply E out by definition of Gn minus. Yeah? Then we're all done. Yeah? Again, this is because the test data points and the training data points, they all have the same distribution, right? Yeah. So now we know that En is an unbiased estimate. What we really care about is actually the ECV, right? The cross-validation error. Let's take a look at the expectation of this ECV. Yeah, that is equal to some kind of a test error, right? We want to show that this ECV is unbiased over this D. Okay. So now, of course, this is equal to ED of 1 over n, n is 1 to n, En like this by definition. Yeah. We can take the 1 over n out and put the expectation inside the sum. This data set D, there are two parts, right? There's a Dn part and then the Xn. Yeah, there are two parts. I'm just write it out. Really not changing anything, right? Okay, there are two parts like that. And they're independent. So since this expectation over two different things, two different random quantities that are independent, then I can write this expectation as a nested expectation. Yeah, expectation over one and then expectation over the other. Okay. So this is equals to E. Let me write the EDN outside, and then EXN inside, like that. We can do this only when it's independent, yeah, because this XN is independent of DN. Okay, because they are totally separate data points. If they are not independent, then inside here you will have to use a conditional expectation, which is quite a lot messier. Yeah. So we already know that EXEN from just above, right, from number 1, this one EN is unbiased. So this one is equal to EN of the test error with respect to GN minus. So this is equal to this. N equal to 1 to N, expectation of EDN. E out Gn minus. Now sounds like we're in a bit of trouble because this thing inside has n, right? Is there any way possibly we can get rid of this sum and so on? We cannot just simply merge things, right? Because these are different things depending on n. Yeah? So this one, how do we connect this to the test error for the entire model? Yeah? So the trick is to define something a bit newer, but also not too new. Yeah? Let's define this bar E out, but it's going to be a function of n. Okay? If we define it as the expectation over the entire data set, this is something that we have seen before. It's the same, in bias and variance, we have seen something like this, right? The test error would be a function of the training data point that you have, right? Because it's G depends on D. Yeah? G depends on the data point you have. So you can talk about the expectation of this test error with respect to the training data point that you have, right? So we can define this as EL, and it is, we put the n here because this G is trained after n data points, right? This is from training over or n samples. Yeah. So that's how we define this EL bar, I guess. Yeah, is the average test error, average over the training samples that you have. Now, why do we define something like that? Can you draw a connection between this one and the one above? This one is E of the entire D, right? G is trained over the entire D. How about the one above? E, the expectation is taken over Dn. How about Gn minus? Gn minus is trained over Dn, right? So these two terms they're very similar. These two, they are very similar, right? What's the difference between them? Just the number of data points you use to train it for training. Right? They have exact same form, right? You train using D, you get G. Over there, you train using Dn, you get Gn minus. Yeah? In the end, you take the expectation over the data points that you have used for training. Yeah? So in fact, the one above, I could just write it as EL bar of n minus 1. Right? Yeah? They have exact same form. So now I can write ED and let's say E out like this is E out minus 1. Yeah. So therefore, we're still trying to calculate number 2, right, the left-hand side. So we're still trying to look for the expected value of the cross-validation error. So expectation over the data set, the cross-validation error, ECV, is equal to that one, but then inside they're all of the same form. And no matter which n you use, they're all equal to the same thing. Yeah? So just the average of that is simply E out n minus 1. Yeah? So in other words, ECV is an unbiased estimate of some test error but that test error is not your regular E out. Yeah? But E out with n minus 1 data points, which is interesting, right? But it doesn't matter though, in big data, n minus 1 and n, they are pretty much the same thing. Yeah, doesn't make any difference. So, which is very nice. So therefore, we know that the cross-validation error indeed is a good measure to use, yeah, because it's unbiased estimate of a test error. Now the question is it still consistent? Yeah, is it consistent? Remember previously we showed consistency by saying that, well, if you take the average of these random variables that are independent, yeah, the variance of the average equals to the average of the variances, right? And then as the number of points we have goes infinity, that average of variances go to 0. But not average of variances, I'm sorry. I should say sum of the variance of the sum equals sum of the variances. And then when you take the average, those averages goes to 0. Turns out that these E1, E2s, they are not independent, right? When we take this average to get the ECV on the top line there, when we take the average of these eons to get the cross-validation error, we would have liked it. We have liked it if the eons are independent. In that case, we have a consistent estimate. But it turns out that they are not, clearly, right? Because when you take one out and then train, take another one out and train, huge overlapping among the two training data sets. Yeah? Clearly, there's a huge amount of correlation between these quantities, yeah, for the entire training procedure and hence the final error. So the error terms E1 to EM, are not independent. So therefore, we cannot say that we cannot derive this that we have been using all the time, that this is not equal to 1 over n of the variance of a En, like that. Yeah, it would have been nice if we had that. So turns out that we cannot prove it. Yeah, we don't know. It depends, yeah, whether your estimate is consistent or not, depending on your problem. However, in practice, people have observed that in practice, the cross-validation variance tend to be small. Okay? Even though we cannot show that it goes to 0 when we have big data. In practice, ECV is often small, kind of. So if it's often when the variance is small, what does that mean? This ECV, we are looking at it as a random variable, right? The ECV is a random variable that is serve as an estimation for the test error, which is that E out of n minus 1. Yeah, we say that the expected value equal to that, and then the variance is small. That means this random variable approximately equal to that constant. Yeah, so which is good. So we still have ECV approximately equal to E out n minus 1. And of course, when n is large, this is the same as E out of n, yeah, which is the test error that we're looking for. Okay? So therefore, kind of half analysis, half hand waving, we made the claim that cross-validation does work, and in general, it actually worked very well, that we really just use cross-validation. Okay? Right. Again, I only have about 15 minutes left of material, so let's just keep going, yeah, without break, and we just end early, and then leave some time for you to ask any questions about the final exam. Okay? Yes?
You said like this stuff that we don't need to remember.
No, this will not be in the final exam. Only for your own interest at this point. Yeah, because in practice we use cross-validation. Usually we don't use the other one. So another interesting connection between cross-validation is with SVM. Okay. The Lu ECV anyways for SVM, leave and out. Okay. What's so special about this leave and out cross-validation when we apply to SVM. Let's see. So again, let's look at a two-dimensional space. Our previous example. Let me erase it. Oh, boy. I want to leave it out a little bit of gap so that it doesn't quite look like a plus there. Same example that we have seen before. We have a minus point here. One minus here. We have at location 2, we have a plus. And location 3, I think, 3 we have a plus. And then here, 2, 2, we have a plus. Oh, no plus, minus. Yeah, that's our previous example. So we are asked to, use SVM on this data set. This toy example, very simple, of course, right? The boundary should look like that. You want to have the fattest margin, so it looks, the margin would be here. Yeah. Something like that. Yeah, that's our margin, and the line, of course, is right in the middle. That's the boundary. Yeah, that's SVM solution. And we know that the ones that sit on the margin, all three of them, they are necessary to hold the margin in place. So they are the support vectors. Yeah, they are the support vectors. Now, for this case, what is the cross-validation error? Of course, it's a 1 over n of n goes from 1 to n, en, yeah? Where en is this, because this is a classification, is a indicator function, that gn minus, that validation point, this one happens to be not equal to the true label, right? Yeah, this will be the en. Yeah, everyone okay? Okay. So now the question is, what is the cross-validation error for this SVM in general? How can we estimate it? Yeah. So now we have to estimate the EMs, right? Take one out, train the system using SVM, and find out what is the error with respect to that data point. Okay. Now this EM turns out depends on whether this n, this sample xn, is a support vector or not. Okay. Turns out that's the only difference it makes, whether it is a support vector or not. Okay. Now suppose it is not a support vector. Suppose this n, the data point that you take out, is not a support vector. What do you think en is? What happens? Just imagine, yeah? Just do this thought experiment. You have a data point that is not a support vector. You throw it out of the training data set, use the remaining data points to retrain your SVM. What happens then? Remember what happens if you throw away a non-support vector? Yeah, nothing happens, right? You throw away this point, this is not a support vector, right? You train the same data points, you still get this same margin, right? Because that is the best margin. You get the same thing. So in that case, what is en? Remember the definition of en, right? What is it? Now this point, the right-hand side point is the validation point, right? You have to check. Under this new solution with n-1 point of training, but which is the same as the old solution, is this data point correctly classified or not, right? For this validation point. What do you think? Is this point correctly classified? Of course it is, right? It was correctly classified before, right? And when you take it out to retrain, you don't change the solution. Of course, now, with this new retrained solution, you still are correctly classified, yeah? So therefore, en will be 0, right? For any data point that is not a support vector, the validation error is 0. En is 0. Okay? So if xn is not a support vector. So we know that training over Dn, it will produce the same thing. As D does. Yeah. So Xn will remain correctly classified. And then this, of course, implies that En equals 0 for all of the non-support vectors. Okay. Now, if Xn is a support vector, now we have to find out what happens. If Xn is a support vector, then of course now, say you take out one of these guys, right? Take out one of those red dots. Of course, your solution will be changed when you retrain using the remaining data points. Yeah? So Dn can be different. In fact, only in some extreme cases it does not. Usually it does. Yeah? It can produce a different solution. And under this different solution, there's no guarantee that Xn is correctly classified anymore, right? Yeah. So, for example, if you take out the middle one here, if you take out this point and retrained, your margin will be here, right? Yeah. The line could have been somewhere maybe here, then this one would be misclassified. Yeah. So you don't know. Okay? There's no guarantee anymore. Yeah. In which Xn, let's say, is misclassified. Okay. So in that case, En can be 0 or can be 1. We don't know for sure, but well, anyway, we know that's less than or equal to 1 because this is just 1 point, right? Yeah. So what conclusion can we draw about ECV? Remember, ECV is the average among all ENs, right? We know that for non-support vectors, it's all 0. So, yeah. Exactly, yeah. Just number of support vectors divided by n. Yeah, at most, the worst case, you have that one, right? And of course, this one is usually small, right? Because the support vectors sit only on the margin. And we know the margin is 1 dimension less than the entire space, right? So the number of points in the regular space certainly will be a lot more than the number of points on the support vector. Yeah? So therefore, this one tends to be very, very small. ECV of SVM is very, very small in general, which is good, right? That's because we know that ECV, the cross-validation error, is a good approximation for the test error, right? If the cross-validation error for SVM is usually very small, then we know that the test error for SVM is usually very small. Yeah, right? When n is large, yeah? So that's the idea, and that's another reason why SVM is a very nice learning model. Yeah, we can use cross-validation to show that it has small test error. Okay. So that's even out cross-validation. Remember what we need to do for even out cross-validation? You take one out, you train, take another one out, you train again, take another one out, you train again. You do this n times. What could be a problem with this procedure? What could be a problem with doing that? Say again? Very slow. Well, in other words, you have to train many, many times. You have to train n times, right? That's impossible when n is large, right? Millions or billions of data points. You cannot train them many times. Okay? So what is the solution? And the one solution is so-called V-fold cross-validation. So let me write it down. The problem is the high total computation. Yeah, because we have to do n times training. The solution, of course, you don't do this n times of training, right? You do only v times training, and this is so-called v-fold cross-validation. How do you guarantee you only do v times of training? First, you just take one out, and then the rest you train, right? So you have to do this n times. So you just want to do this v times. So every time, how many data points you have to take out? You have to take out n divided by v, many data points every time, right? You just separate your data points into v groups and do the same thing. Yeah, so that's the idea. You split d into v equally sized validation sets. Yeah, so d would be, say, let's call it D1 union D2, DV, I'm sorry. DV, yeah. So in general, because usually n is large, right, you can safely assume that n divided by v is close enough to an integer, yeah. Just say an integer. Even if it's not, no big deal, right? Missing 1 or 2, just by a small fraction, doesn't matter. So after that, you just do the same thing for m equals to 1, 2, to v. Yeah, you just repeat v times. You take the mth one out. So the remaining one, the dm of training, will be d1 union, union. Here we have to jump over dm, right? So let's write dm minus 1, then union dm plus 1. And then until you get to the vth one, yeah? And then, of course, you're going to use this one to train. Model to obtain a hypothesis that we call it G of M. And then now, of course, now you can let E of M, not per sample cross-validation error, but rather per group validation error, is this N over V. Yeah? I'll just write like that. Summation over Xn is in the M's group. Yeah, this Gm of Xn, Yn, yeah? Just like that. Yeah? Nothing really surprising, right? So you keep doing this, you get the Gm, then you have the V-fold cross-validation error. Now just take the average of that. ECV 1 over V. Yeah. M goes to 1 EM. Yeah? So, yes?
So this is still pretty slow. So would you ever use this in practice? Because like if you're training a big model, right?
Yeah, it's a trade-off. We do. If V is not too big. Yeah. So for example, you choose v equal to 10. That's a rule of thumb, basically. Yeah, a common value. So you only do this 10 times. Common choice. So v equals to 10. Okay. Yeah, and if that's the case, what does that mean? We have n over 10 fold reduction in the training time. Yeah. Right. But what is the disadvantage compared with a leave and out? You always have to give something to take something. Yeah. So what do we give up? Yeah. Yeah, because, well, no, actually, no, not easily less accurate. No, there's another thing that's less subtle than this. The training is less accurate. Why is that? Why is our training less accurate? Yeah, we have less data now. We only have 90% of the data left, right? So we have 10% less data for training each time, yeah? But that's something that you have to give up, yeah? So there's a trade-off in general. So usually we go somewhere in the middle, right? So you just do k, split once, k, and then n minus 1. That's almost like just do it once, right? But here you train 10 times, but then you lose maybe less data point. You only lose 10% of data points. Instead of say maybe 20% of data points. Okay. So that's it. That's the general form of cross-validation, and also that's it for the entire semester. It's been fun having you all here, and I'm very happy that you're all here, knowing that this is not going to be in the final exam. You're all here because this stuff is interesting, right? So I'm glad to see you here. Now, any questions about the final exam at all? Yes?
Just like in general, what areas should we focus on?
It will be mainly after the midterm, okay? But obviously, you still need to be very familiar with the material before the midterm. For example, you have to know linear classification to do SVM, right? And things like that. But most of the questions will be focusing on the second half of the semester. Yes, I already posted them on Quarkus. Will be similar, yeah. Okay. All right, good, thank you. Yeah. Proofs, yeah, maybe, yeah. I think it's a valid exam question, but very simple proofs for toy examples. Kind of like in the midterm exam, prove that this one, whether yes or no, not linearly separable, that kind of thing. Yeah. Okay. All right, no more questions. Then I'll see you either in my office hours or in the final exam. I still have the remarking. Anyone else has the remarking request? No, you have. Are you in this section though? Oh, okay, I see. Yeah, I did not bring it. Yeah. I received the part back. Yeah. Okay. Good. All right.
I have a question about